Last week we talked about the expectation, and today we will look deeply about the expectation. Okay, so we know that expectation. We learned that expectation is to consider all possible outcomes. So all possible outcomes times their corresponding weightings. Okay, that is the way we learn that. But today, you will see backward. If I have this integration, you need to know how to interpret it. Consider all possible outcomes times their corresponding weightings. That is the expectation. Okay, so first, let's do this integration. What is the integration of e to the minus x squared dx? In the past, when you done calculus, then you set up like I equals this, and you combine both. But this time, if you see e to the x squared, okay, so we can rewrite it. Let's have e to the minus x squared divided by 1. That means I can divide by 2 times 1/2. Okay. And then I also times additional term called 2 pi times 1/2. And then I need to compensate this, so time this back. 2 pi times 1/2. What is this integration? This integration, don't you think that's familiar? This first, this is Gaussian, right? It's Gaussian, normal distribution. What is the mean? Mean is 0. And variance 1/2. Okay. Why? Because this is your fx. So if this is fx, then what is the integration? By your properties of your PDF, you do the integration, you consider all. Then this goes to 1. So if this goes to 1, then you get your integration, that is pi, square root of pi. The other one, I also do the integration, 4x squared e to the minus 2x dx. So here we can also rearrange that, since we see first it is from 0 to infinity, not minus infinity to infinity. 0 to infinity, and also I don't have x squared term for the exponent. My exponent is 2x, so e to the 2x minus 2x. So let's just rearrange this as 2x squared 2 times e to the minus 2x dx. Right, so what is this term? 2 times e to the minus 2x. And also I do the integration from 0 to infinity. This is the exponential distribution with the parameter 1/2. And I times x squared. So if you know this is exponential PDF, then you can change that to x right? I have x squared times f of x. What is this? You can put 2 outside. X squared times f of x, and integration from 0 to infinity. Consider all possible outcomes, function of possible outcomes times your weightings. Then you have 2 variance plus the mean squared, right? Because this is second moment. Okay, and then now you know this exponential distribution, then we know the variance, we know the mean, and you can find the answer right away. Okay, you don't need to do the integration by parts twice. Okay, because now you have already learned probability, you should use this concept to find the integration. So this gives you 2, your variance 1 over 2 squared, your mean 1 over 2, and mean square 1 over 2 squared. So you get 1. Now let's see another example. If I have an integration from minus infinity to infinity, x times e to the minus x squared over 4. Okay, you can think about this. Let me give you 1 minute and try to figure out the integration using the probability concept. We still need to observe it is the integration from minus infinity to infinity. And I have exponential. The exponent is x squared. Okay, so since this is x squared, then we may think about Gaussian. If this is e to the just minus x, then we may think about exponential. So here we have x, and then e to the minus x squared divided by 2 times 2. And here I have additional term divided by 1 over the square root of 2 pi times 2. And then we times this term back, 2 pi times 2 dx. And now what is the answer for this? Here we know this is the Gaussian distribution, right? For the Gaussian distribution, then we want to know what is the mean, what is the variance. This is Gaussian distribution, so the mean here is 0, variance is 2. So now what is this integration? Here you can see that this is the PDF, right? So we have consider all possible outcomes times your PDF, and this term will be your expectation. Now this is the expectation of your Gaussian distribution. Then the mean is 0. So actually this integration is just 0. Next, then how about this integration? E to the minus x plus y plus z squared over 2, or over 1. dx. Then you try to find this integration. What is the result of this integration? This one should be square root of pi. It is exactly the same as the first example, because now I'm doing the integration with respect to x. Okay, so here, whatever here it is, that will be your mean. Okay, and your variance is still 1/2. Okay, and overall, by the properties of a PDF, this will be 1. Okay, so no matter what your mean is, you have y, z, w, d, whatever those mean, it doesn't matter, because here the integration will be 1. So you'll get square root of pi. Okay. Last one, this is just the integration, right? How about the summation? Let's see this summation. K from 0 to infinity, x to the k over k factorial. And here you see factorial. You may think about the Poisson distribution. Okay, so k from 0 to infinity, let's rewrite this, x to the k over k factorial. Let me times e to the minus x, and then times e to the x back. So this will be the same. They will cancel out. Then what is this term? This is Poisson distribution. Okay, so no, the PMF of Poisson variable. Okay, if this is a PMF, then I do the summation from 0 to infinity. Then this becomes, by the properties of PMF, this part will be 1. So you get e to the x. Then today we focus on function of one random variable. And then later on we may talk about multi-random variables, which means more than one. We have 2 random variables. First, let's see this question. Given x, this is a random variable. Since we said this is a random variable, then we should know their CDF, their PDF. And we also have another random variable called y. And y is a function of random variable x. Then since y is a random variable, I also want to know the CDF and the PDF. So it looks like I have a sample space. Here is the sample space. And I have omega. Now I map to the real line. This is x omega. I have a random variable x. And I can also map this realization to another real line. Let's use group. Okay, this that means if I map the realization to another real line, we can think of this realization map to the x, the real line for x function, And then x function map to another function, the x map to another real line. So if I map to another real line, there's a function called g. And here you have random variable y. So this green is that I have a random variable y that is through the function g of x. Right, so now we can think of this random variable, the realization. They map the real line that is for the random variable x. From the random variable x, I can also map to another real line using the function g. That means I can directly have this realization map to the real line, and that is the random variable y. Let's just see this example. Suppose we know the CDF and PDF of x, and then I have a relationship between y and x. Then I want to find and I know that y is a random variable. So I want to find the CDF and PDF of y. What is the CDF of y? Which one you want to find first? It's better to, well, there's no preference, but if you get the CDF of y, then you take the derivative of your CDF, you can get PDF of y. So let's just find the CDF first. So f of y, what is the CDF of y? According to the definition, CDF is the probability. And this probability is the random variable y less than or equal to some point. Here we just say lowercase y. Okay. And what is random variable y? This random variable y is 2x plus 3. So that means 2x plus 3 less than or equal to certain point y. We can simplify it. That will be x less than or equal to y minus 3 divided by 2. What is x? What is the probability of your x less than some point? This will be the CDF of x. So this is the CDF of x. And which point? Y minus 3 divided by 2. Then this is the CDF. How about the PDF? PDF, just take the derivative of the CDF. And we just found our CDF, Fy. This is the CDF of x at y minus 3 over 2. And we can use chain rule. For chain rule, f of x, y over 3, y minus 3 over 2, and here with the y minus 3 over 2. Having the chain rule, let's see the first term. What is first term? D CDF of x something dx. In this case, this will be the PDF of x. So this is the PDF of x. At y minus 3 over 2. And then times the second part, you'll get 1/2. So now we can see that I have a random variable x, and this random variable x, I send it to a channel. This channel is the function g. And later on, we get a new random variable y. So actually, in many engineering systems, we need to transform one quantity to another. We may see some examples later. And in general, that we are interested in finding the CDF and PDF of the random variable y. And the g function is an arbitrary function of x, and also x is a random variable. When x is a random variable, then we have the PDF and CDF. And we assume that we know the PDF or CDF of the random variable x. Now, how do we find the CDF of y and PDF of y? Okay, we know the methods, and actually here we just look into it. We have two approaches to find the CDF or PDF. Well, actually, to find the PDF, we have two methods. Here we have basic approach and also direct PDF method. Let's see. Suppose now y is a function of x, and it is a monotonically increasing function. So this is x, and this is y. And here, okay, so now first let's see. CDF of y, by the definition, we know that is CDF is probability of your random variable y less than or equal to certain point. Okay, some point here we put y. You can put anything, like you can put smile face. Okay, some point y. What is y, this random variable? It is g of x. So that means g of x less than or equal to some point y. Now, since this function is monotonically increasing, that means if I have y here, well, monotonically increasing, that looks like this function, g of x. So here I have a y, then the corresponding x is g inverse of y. That is your x. And they say that gx is less than y. Gx is less than y, it means here. And your y so if I want to get less than y, here y is this point, so less than y. To get less than y, then my g inverse of y should be in this region. G of x, that means if I times the inverse to both sides, we have g inverse of g of x less than or equal to g inverse of y. What is the left-hand side? G inverse of gx, that is just x. And then right-hand side, that is g inverse of y. So that's why that my x should be less than g inverse of y. So this part. And what is the probability of your random variable x less than some point? Now, probability of your random variable x less than some point, that is the CDF, right? So here is the CDF of x, where g inverse of y. So now this is the CDF. Okay, we found the CDF. CDF of y is the CDF of x at g inverse of y. Then what is the PDF of y? To find the PDF of y, so the basic approach is that I find the CDF and then I take the derivative to get the PDF. So I take the derivative of my CDF of y, and we found that the CDF of y is f of x at g inverse of y. Then we use the chain rule. So for this chain rule, I divide it by d g inverse of y, and that times d g inverse of y in the numerator. What is the first term? You can think about this is just like an x. Here is the x, right? Then the first term will be your PDF of x. So here is your PDF of x. And then the second term, g inverse of y means x of y, right? So this is the PDF of x. We have PDF of x times the derivative, and we have this as a equation 1. So now let's see an example. Y equals g of x, and actually it is ax plus b, and my a is greater than 0. First, using the basic approach, we need to find a CDF, and then take the derivative of your CDF to get PDF. So first, what is the CDF of y? Always use the definition first, and then you try to how to manipulate it. So what is the definition of your CDF? Probability. Probability of your random variable y less than or equal to some point y. Now you can change y to x. That is ax plus b. So ax plus b is less than or equal to y. And this, just simplify it a little bit more. I have x is less than or equal to y minus b divided by a. And what is the probability of your x random variable less than or equal to some point? This will be your CDF of x at y minus b over a. This is your CDF. So now let's see the PDF. You take the derivative of your CDF of y. So here is the PDF of y. You take the derivative of your CDF. That is CDF over x at y minus b over a dy and changing variables. So you have the y minus b over a, and then the y minus b over a dy. What is the first term? You see, this could be x derivative of your CDF over x. That is your PDF over x. And then second term, you get 1 over a. Okay, we can also draw this relationship. Here is x, and then here's y, and I have y equals ax plus b. A is greater than 0, so this line is g of x equals ax plus b, and my a is greater than 0, so the slope is positive. I have a point y here, and their corresponding x is y minus b over a. The less than y is less than y, so ax plus b is less than y. So this part, let me give it a green. That means this area, this region. Now, we assume that this is monotonically increasing, but how about the function g is monotonically decreasing? If it is decreasing, let's draw this decreasing function here. Monotonically decreasing like this way. Okay, so to find the CDF of y, that means the probability. The probability of your random variable y less than or equal to some point y. And what is the random variable y? A function of x. So this is gx less than or equal to y. And we can take the g inverse from on both sides. So you'll get probability of your g inverse of gx of gx, and the right hand side is g inverse of y. But now let's see, if my y is here, this is my g inverse of y. Your g of x is less than y. Now it's this part. Okay, so for this part, my x is here, right? So I would need to change sign. This is greater than or equal to g inverse of y. And this is g of x. So you can see that gx is less than y here, this part. Gx is less than y. That means g inverse or this x should be greater than or equal to this point. My x should be greater than or equal to this point. Okay. Left hand side, that is your random variable x. It should be greater than or equal to g inverse of y. Well, now I still have a probability. This probability is x greater than or equal to something, not x is less than or equal to something. So how do I make this expression into the CDF? From the probability axiom, if the probability of your random variable x greater than some point, that means it is equal to 1 minus the random variable x less than or equal to that point. So it will be 1 minus CDF for x at g inverse of y, which means 1 minus f over x, x of y, because we know x of y is g inverse of y. Then this is the CDF, the PDF, taking the derivative of your CDF, we get d1 minus CDF over x divided by dy. We have minus PDF of x n times the derivative Let's continue for this example. Now, since a is less than 0, so this function is monotonically decreasing. Then what is the PDF of the variable y. To find the PDF, we find the CDF first. So the CDF of y is by the definition, that's the probability. The probability of your random variable y less than or equal to some point y, and we just replace y by ax plus b. Now let's plot a plot here. This is x, and here is y. And this is the function, the line. G of x is equal to ax plus b, but a is less than, one more time, ax plus b, and a is less than 0. And I have a point, some point y, suppose here. And the corresponding x is y minus b over a. And when ax here, ax plus b, this gx is less than y here. That means my x should be greater than this x point, should be this part. So here the x should be greater than or equal to y minus b over a. Okay, let's see that again. Ax plus b less than y. So ax plus b less than y, this point will be here. Right. So here, that means my x should be greater than this point. So ax plus b is in this line. Okay. So if I have a greater than or equal to, it means this probability is equal to 1 minus probability of your x less than y minus b over a. Which is the CDF of x at y minus b over a. Make your PDF just by taking the derivative of your CDF. And what is your CDF? 1 minus your CDF of x. At this point, 1 minus b over a. Using the chain rule, we have minus the CDF of x at y minus b over A divided by dy minus b over A. So the first term is the PDF of x, y minus b over A, and times 1 over A. So now after seeing these two examples, let's combine equation 1 and 2. You can see that equation 1 and 2 are really similar, just have a different sign. So if I combine equation 1 and 2, we have a theory. The random variable x is a continuous random variable, and we have a PDF of x. And a random variable y is defined as a function of random variable x, and it is monotonic function. It could be either increasing or decreasing. Then we have this formula. How do we find the PDF of y? I have a PDF of x times this, we can say as a Jacobian, but this is the absolute value determinant or absolute value of your dx over dy. And then what is x of y? X of y is the G inverse of y, and it is the x written as a function of y. This is also our second method, direct PhD method, to find our PDF. Let's see the proof. The PDF y for the monotonically increasing equation 1, we found actually the PDF of y is the PDF of x of x of y times d x of y dy. This is just equal to our theory. We can also take the absolute value. Because that term is greater than 0. This is greater than 0. Greater than 0. And this is monotonically increasing. Monotonically increasing. And how about the other case, monotonically decreasing? The equation 2. For the equation 2, we have a minus sign. And it still can be written as your PDF of x times the determinant, the absolute value. of your dx over dy. And dx of y dy is less than 0. And this is monotonically decreasing. So overall, y equals ax plus b, and we just say a is not equal to 0. It could be greater than or less than 0. Then my PDF of y is the PDF of x at y minus b over a times the absolute value of 1 over a. Here is another example. X is an exponentially distributed random variable, and we have the PDF. And y is a square root of x. Now let's find the square root of y. Now let's find the PDF of y. We need to observe and check. This function is monotonically increasing or decreasing or not. So y equals square root of x, and that is the function of gx. It is monotonically increasing. The PDF of y, that is the PDF of x of y times the absolute value of d of xy over dy, and then in this case d of xy over dy is dy squared over dy, that is 2y. Then here's a note for y equals square root of x, which means x is y squared. And my y is always positive, since y takes positive values only. So only positive values. We note the x of y only takes on positive values. Therefore, f of y is the PDF of x of y squared, and then absolute value of 2y. My y is greater than 0. Then this is PDF of x at y squared. So we have alpha e to the minus alpha y squared times 2y times, now y is greater than 0, so I can either write it on y is greater than 0 or use the index function. We can also express that into two parts. It's either 2 alpha y e to the minus alpha y squared. The y is greater than or equal to 0. The other one is 0 otherwise. And this distribution is called relay PDF. So here's a note. If we say 1 from A to B of x, that means either 1 or 0. You have 1 when your x is between that region A and B. Otherwise, it should be 0. Okay, this is the method that we use called direct PDF method. We can also find the CDF first and then take the derivative to find the PDF. So we can check it. We can also find the CDF first. And take the derivative, to get the PDF of y. So here's the CDF. What is the CDF? Again, by the definition, the CDF is the probability. So the CDF of y is the probability of your random variable y less than or equal to some point y. What is your random variable y? That's square root of x less than or equal to some point y. And then we can rearrange that the x becomes a square root of x to x less than or equal to y squared. What is the probability of a random variable x less than or equal to some point? That's the CDF of x of y squared. Now we have the CDF. Let's take the derivative of the CDF. You should get the PDF of y. And we use the chain rule. Then you get the PDF of x, y squared times 2y. And your y is greater than 0. Now you may ask, why do we need this function to be monotone? Because the monotone function is 1-to-1. So that 1x I can correspond to 1y. That means the x equals g inverse y is unique. So here the answer. Monotone function are 1 to 1. That means there's only one x corresponding to each y. So we can write the x of y equals g inverse of y uniquely. So what if this function is not monotonic? So what do we do? What does that mean, that not monotonic? Let's draw this function. For example, this is x. This is y. Suppose we have this function. This is y equals g of x. Here we have y. Y plus dy, say here. Here. So here I have x1. This is x2. X2. Here is x2. And this is x3. For this part, it will be x1 plus dx1. x2 plus dx2. And then x3 plus dx3. If I plot y only, this y, we can map this y All right. Okay, so now suppose we have a function. It is not monotonic. Okay, you can see that it is increasing and decreasing, increasing. So suppose I have a y here, and plus a little increment. So y plus dy here. Then what is the probability of this random variable y between these two? And then in terms of x. Okay, so this corresponding to this part, if this is the PDF of y, then this area, what is this area? This area is Anyway, for this area, that is the probability of your random variable y between 2 points, y and y plus dy. All right, so now to find this area, okay, this area, that means in x, this part, and this part. Okay, so here, and here. So there'll be, my x is between x1 and x1 plus dx1, x2 and x2 plus dx2, x3 and also x plus dx3. Okay, and you can see that those regions are disjoint interval. Disjoint interval. So since it is disjoint interval, then union becomes summation. Plus probability. My x is between x2 and x2 plus dx2. And the probability. X is between x3 and x3 plus dx3. Then here that means this is my x, and this is the PDF of my x. So the PDF, and we have x1, x1 plus dx1, x2 plus dx2, x2, and then x3 plus x3 plus dx3, x1, i.e. x1 plus dx1, x2 plus dx2, x2, x3 plus dx3. And then we have the region. Okay, so I want to find those regions. First, for this probability, that is probability y, variable y, random variable y is between y and y plus dy. That is the PDF of y, dy. Okay, I want the area, okay, and here's dy. And then for x, probability of x is between x1 and x1 plus dx1. That is your PDF of x at x1 times dx1. And the probability of your random variable x between x2 and x2 plus dx2. That is the PDF of x2 times dx2. Similarly, for x3, so I have a PDF of x at x3 times dx3. So in terms of the PDF of x and y, then we have the f of y dy. That'll be f of x at x1 dx1 plus f of x of x2 times dx2. And the last term, f of x at x3 times dx3. Therefore, finally we can find our PDF of y. That is your f of x at x1 of y dx1 of y over dy. And for x of x2, similarly, like in each part, you just do the direct PDF method, your PDF of x times the absolute value of their derivation. Let's see this example. Y equals x squared. Therefore, y equals x squared. Let's plug it first. Then here is y, suppose here. This is g of x. And then here we have x1 of y, that is square root of y. Here's x, here's y. And this x2, suppose it's called x2 of y, that is minus square root of y. So to find the PDF, first let's use a direct method. Okay, and since it is not monotonic function, so we have two parts needs to be considered. The PDF of y is a PDF of x. First part is increasing part, increasing monotonically increasing function when x is greater than 0. So x1 of y times their derivation, dx1 of y dy. And then the second part, x2 of y dx2 of y dy. If y is greater than 0, less than 0, we know the PDF is 0. If y is greater than 0, then dx1 of y dy, using the chain rule. We don't need the chain rule. We get 1 over 2 times square root of y. Your dx2 of y dy will be minus 1 over 2 times square root of y. So your PDF of y, that's f of x of square root of y. Okay, so here we have 1 over 2 times square root of y times your PDF of x at square root of y plus the PDF of x at minus square root of y. And the y should be greater than or equal to 0. So y is from 0 to infinity. We can also find the CDF of random variable y and then take the derivative to get the PDF. So let's see another approach. So here, the CDF of y, that is the probability. By definition, probability of your random variable y less than or equal to some point. And what is y? Here in this example, that is x squared. x squared less than or equal to y. And we can take the perfect square out. Then my x actually is between minus square root of y and square root of y. And this is the CDF of x at square root of y minus the CDF of x at minus square root of y. Then you take the derivative. So you still get f of x at square root of y, and then times 1 over 2 times square root of y. And the other term, the PDF at minus square root of y times 1 over 2 times square root of y. Okay, so next example. We will take a break. So for next example, you can take a look and you can try to find the PDF of y using both methods, and then we will compare. I want to find the PDF. Overall, it's just two ways. You find the CDF first and then take the derivative, or you use the direct method. So here, let's see. We still do, for examples, we still do these two methods, and you can choose which one you prefer. First, find the CDF. What is CDF of y? That is the probability. So probability of your random variable y less than or equal to some point y. And then we replace y by the example here, e to the x. And then we can rearrange this, simplify that as x less than or equal to natural log y. What is the probability of your x less than or equal to some point? That is your CDF of x. Then to get your PDF, you take the derivative of your CDF. And then you also need to use the chain rule. So here it is the chain rule. That gives you first, that's the PDF of x at natural log y. Second term, you get 1 over y. So we know that our PDF of x is exponential distribution. So here we have minus lambda y times 1 over lambda, or 1 over y. And then the indicator function, because y is from 0 to infinity. The second one, just use the direct method. So identify the function g, that is e to the x, monotonically increasing. So y equals e to the x means x is equal to natural log y. And then your PDF of y will be your PDF of x of y. And then dx of y dy. So that's f of x at natural log y times 1 over y. That gives you e to the minus lambda y, 1 over y times the indicator function. We can also plot this function. Here's x, here's y. And then e to the x, this is g of x. And at y-axis, this is 1. All right, next, we'll talk about how do we generate the random numbers on computer. In MATLAB, we have the built-in functions like Gaussian, exponential, uniform, which is good. But if you want to generate an arbitrary PDF, how do we do it? Here's the theory. X is a random number, and we have invertible CDF. If my random variable y is the CDF of x, then this random variable y is uniformly distributed from 0 to 1. Let's prove this. Uniformly distributed means, okay, I have a random variable u that is uniform from 0 to 1. This means the PDF is 1. And this u is between 0 and 1. And then the CDF of this random variable, let's take a look. The CDF is the integration of your PDF from minus infinity to the u, this point. Okay, so for the uniform random variable, the CDF is u. And again, u is between 0 and 1. If the random variable y is the CDF of x, Let's find the CDF of y. What is CDF of y? That is a probability of your random variable y less than or equal to some point, say y, lowercase y. That is the probability of your CDF of x less than or equal to y. Which means my random variable x is less than or equal to the inverse CDF of x at y. We saw this many times today. What is this? Probability of your random variable x less than or equal to some point. That is the CDF. But here it is the CDF of x. Then gives you y here. And now you see the CDF is y, then y is uniform. Okay, if it is a uniformly distributed random variable, the CDF, it should be f of something that should equals to something. So this is uniform. Okay, so now here is the procedure for generating the random variables. We generate the random variable uniform. Okay, because we have the uniform random variable in MATLAB. And then with that, y equals inverse of your CDF of x of u. Then your distribution will be the CDF of x. Let's see. Why do we need the inverse of CDF of x? First, what is the CDF of y here? That is the probability of your y less than y, which is probability of your inverse CDF of x less than y. And here is the u random variable u less than or equal to the CDF of x of y. Probability of random variable less than something, that is the CDF of that random variable, which is CDF of u at f(x) of y. We know u is uniform, so the CDF of u here, the CDF of u by the previous example, this should be f(x) of y, the CDF of x at y. Okay? So this is the CDF of x of y because it is uniform. Okay, so for example, to generate the exponential distribution, we will first generate the uniform random variable. Generate the U random variable that is uniform from 0 to 1. And then we need to find the inverse of your CDF of x. And then x is exponential. So we know if x is exponential, the CDF of x is 1 minus e to the minus lambda x. Then the inverse is minus 1 over lambda natural log of 1 minus x. And then you let your random variable y equals the inverse of your CDF of x. Then the distribution of this random variable y is exponential. Now, so far we just learned one random variable, which is discrete and continuous. And then today we learned a function of this random variable. Then the next is that how about two random variables? Or even three or more. So here we have multiple random variables. And now we just focus on two. For two random variables, we still want to know and also be interested in their PDFs and CDFs and how do we find the mean or the variance. And also that what does that mean, that two random variables? Given a random experiment, two functions, x and y, are assigning two real numbers. So I will map the sample space to the real line. Sample space to the real line. We get x zeta and also y of zeta. And we call that this is the two jointly distributed random variables. So we can see I have a sample space. I have zeta 1, zeta 2. Those are the realizations, which means the outcome. Maybe I put here this way. Now I map this outcome to the real line. So here, suppose I map this to the real line. This is x zeta 1. And here, x zeta 2. Zeta 2. And for zeta 3, I also have a map. But I can also map these realizations to another real line. Say Here I have y of zeta 1. And here is y of zeta 2. And the last one, y of zeta 3. We can think of this as an xy pair. The joint distributed random variable x and y gives a pair of a real number. So here we can think about this mapping into. I need to plot the sample space again. This is the sample space. I have a zeta 1 and zeta 2. Instead of mapping to two real lines, I can map it to a plane, an xy plane. So using purple, x1, a zeta 1 to this point we call x zeta 1, y zeta 1. Maybe here, that's x zeta 2, y zeta 2. And for this map is the, I think I can write here, x and y will be from the sample space to a plane, R squared. So we can think of the pair of random variables mapping from the sample space to a plane, or just for two real lines. Let's see an example. Here I have a sample space. This sample space is from 0 to 2 pi, 0 to pi, and we have a theta. First, theta map to cosine. This will be x of theta, that's cosine theta. And I can also map this theta to sine, which is y theta, that is sine theta. In that case, in the plane, I have x and y. And here is a theta I. We have theta, and this is x of theta. Here's y of theta. Now we have two random variables. Of course, we are interested in what their CDF or PDF are. Here is a definition for their CDF. And for this CDF, we call Joint CDF. X and Y are two random variables. The joint CDF of xy, you can see this function f of xy. CDF always the probability. It is always the probability. So CDF, even though it is joint CDF, and that is the probability. And here the probability is the probability of the x less than or equal to some point intersect the y also less than or equal to some point. Okay, also means that there's a realization or outcome from the sample space such that the mapping in the real line that is less than or equal to some point x and also intersect for the case in y. In the real line that is less than or equal to some point y. And the joint CDF gives a complete probabilistic description of a joint behavior of your x and y. Let's see some properties of the joint CDFs. CDF, again, it is a probability. So the probability is always between 0 and 1. And then what is this 2? The CDF x is minus infinity. Why? If x is minus infinity, this is minus infinity. What does that mean? This is minus infinity. Intersect the y. This part is an empty set. Intersect something will be still an empty set. So this CDF is 0. And then if they are both infinity, they include everything, then the CDF is 1. Because probability of your x less than or equal to infinity intersect the y is also less than or equal to infinity. This is sample space. This is also sample space. Then the probability is sample space intersect sample space. It gives you probability of your sample space. And of course, this is 1. Next, since it is probability and also CDF, the joint CDF is the same, non-decreasing function of both x and y. Now, let's figure out what CDF this is if my x is infinity. So if my x is infinity, let's see, x is infinity, that means it is a sample space. So overall, that is the probability of y less than or equal to some point y. This, what is this? This is the CDF of y. And similarly, if y goes to infinity, this is the CDF of x. And for these two examples, this is called marginal CDF. This is called marginal CDF. Okay, so now this is the CDF. How about the PDF? For PDF, we have continuous and discrete. So we have joint PDF or joint PMF. Okay, we say that this joint CDF. This is the joint CDF of x and y. Then what is the joint PDF? Taking the derivatives. We know that for this PDF, you can take the derivative of your CDF to get it. Similarly, we take the derivatives, but now we take the partial derivatives with respect to x and y, then we get the joint PDF. I have x and y, they are two continuous random variables. We can also get the joint PDF by doing the integration. No. With the joint PDF, I take the integration, I get the probability. Okay, so how do I find the probability? If I have a joint PDF, I take the integration. It's kind of like finding the area, right? So here my x is between a and b, y is between c and d. So it should be a and b. For discrete case, PMF. The joint PMF, we know for PMF, when we learned the PMF for one random variable, that is probability. So for joint PMF, that is also the probability. And this probability is that x is equal to some point x, and also y is equal to some point y. Now let's see the properties of this joint PDF and the joint PMF. First, the joint PDF or PMF should be greater than 0, especially for the joint PMF because it is probability. So that should be greater than 0. And what is this integration from minus infinity to infinity of your joint PDF? Similarly to our PDF with one random variable, this integration should be 1. Okay, I consider the areas. I include all the probabilities for discrete case. I sum them together, it should be 1. If x and y are discrete, then we write the joint PMF as the summation, double summation, your PMF, the CDF of xy. We consider the joint PMF at x prom, y prom. And here we have y prom less y prom less than or equal to y, x prom less than or equal to x. And if x and y are continuous, well, how can I find the CDF, the joint CDF? You also do the double integration of your PDF of xy, x prom, y prom, dx prom, dy prom. And the integration is from minus infinity to y and x only. If you go to the infinity, then this integration will be 1. Like here. Okay, if it goes to infinity. And last, let's see if x and y are discrete, how can I find the marginal PMF? And for continuous of x and y, then what is the marginal PDF? So marginal PMF for discrete random variables, For x, marginal PMF of x, that means I don't want the variable y. I only have x. Okay, so if I don't want y, I just sum y out here. I put y, then you get the PMF of x. If you want to find the PMF of y, that means you don't want x, so you can sum x out. So x, y, then you get PMF of y. So similarly for continuous case, I want the PDF of x. So if I want the PDF of x, which one I don't want, x or y? That should be y. So I integrate y out from minus infinity to infinity. There'll be the f of x. If I want to find the PDF of y, then I don't want x. So I just take the integration with respect to x. And then I get the PDF of y.